Okay, we are continuing our discussion of fluid dynamics or fluid flow, right, moving fluids. And we're going to talk about one of the most important equations you'll learn in this class, which is the Bernoulli equation. This is an equation that tells you how the pressure in a pipe changes based on changes in the area of the pipe, based on changes in the height of the pipe, etc. So it's a critical equation for designing a skyscraper where you need to pipe water up onto the top floor of the skyscraper. It's really important in a medical field when you need to figure out how does your heart pump blood up into your head. In all sorts of fields, the Bernoulli equation comes into play. So let's go back to our example of the hose. And we already discussed that the volume flow rate in a hose stays constant. So that when you put your finger on the end of the hose, in order to keep the volume flow rate constant, the speed of the water coming out of the hose actually increases. Okay. And so the question is, if the speed is increasing, the kinetic energy is also increasing. So where is this energy coming from? Are we just suddenly making energy out of nothing? That can't happen. So where is the energy coming from? And it's a bit surprising, but it turns out the energy is related to a decrease in the water pressure. So the increase in the kinetic energy of this water coming out of this hose is related to the decrease in the water pressure that occurs when you press your finger on the end of the hose. Okay, and so that may be a little bit surprising. In fact, it may be your intuition that the pressure would be increasing when you put your finger on the end of a hose, but it's not the case. In fact, you're decreasing the water pressure in the opening, and that's causing the water to come out with greater speed. Okay, to understand that better, we need to introduce the Bernoulli equation. So here's my favorite form of the Bernoulli equation. I'm going to show you a few other forms later. And at first, it looks like a big equation, but we can understand each of the different terms. Right? And they're all labeled here. So the first term is the pressure at point 1. So I have water flowing through this pipe. I'm going to pick two different locations, point 1 in the pipe and point 2 in the pipe. So the pressure at point 1 in the pipe is this term. This term is the density, rho, times g, times the height of that point in the pipe. So this y1. Okay, and this term is 1/2 the density times the velocity of the water in the pipe at point 1. So the water in this part of the pipe is moving at some velocity. So that's all the terms on this side of the equation. On this side of the equation, we have the pressure at point 2. I'm sorry, that's mislabeled. Let me fix that for you real quick. Pressure at point 2, there we go. There's point 2. This term is the density of the water times g times the height of point 2. And this term is 1/2 the density of the water times the velocity of the pipe at point 2 squared. All right, so this is Bernoulli's equation. It's telling us that this sum of quantities is constant, meaning this sum of quantities at this value at this point has to have the same value as this sum of quantities at this point. All right, so this will allow us to solve for an unknown. If I know the pressure at point 1, I know the height, I know the velocity at point 1, and I want to know what's the pressure at point 2, well, all I need to know is the height of point 2 and the velocity at point 2. Okay. To understand this equation a little bit more, let's think about where this equation really comes from. This equation is actually a statement of energy conservation, right? But instead of writing down it as energy, it's actually described as an energy density, energy per unit volume. So really another way of saying Bernoulli's equation is this is the net energy density at point 1 is equal to the net energy density at point 2. Right? And we have energy conservation, so as you increase in height, maybe the potential energy density increases, something else has to decrease. Right? For example, the pressure would decrease. In order to keep the energy constant, the total energy density has to be constant. To understand a little bit more about why this is an energy density, let's look a little bit at this equation. And let's look first at the pressure. Pressure we know is force divided by area. Right? So the units of that is newtons per meter squared. And let's actually make a little trick here. Let's multiply the numerator and denominator of a pressure equation by distance. Okay, so the numerator now is force times distance, which is newtons times meters, and the denominator is area times distance, which is meters squared times meters, or meters cubed. Okay, so looking at that a little bit more closely, Newton meters is the same thing as our unit for work, right? Force times distance is work, or related to energy, right? And meters cubed is a unit of volume. So pressure is really also energy per unit volume, or joules per cubic meter. So we could write pressure in terms of newtons per meter squared, or we could write it as joules per cubic meter. So pressure is really also an energy density, right? And so if you look at all these different terms, all these terms are now energy density. The pressure is just an energy density. This is rho g y. This looks like a lot like mgy, like our gravitational potential energy. If I just divide m by volume, I get density, right? So this is just my gravitational potential energy density, and this term looks a lot like 1/2 mv squared. Again, m divided by volume is just density, so this term is just my kinetic energy density. So Bernoulli's equation is really just making sure energy is conserved. We're basically adding a new type of energy. Pressure is an energy density. It's a way of storing energy. If you have a high pressure object, again like a super soaker, you could store a lot of energy and you can turn that into kinetic energy later. So pressure almost acts like a potential energy. You can store energy with pressure. So okay, there's 3 ways to write down Bernoulli's equation that are all, I think, useful in different cases. They're all helpful in terms of just a conceptual understanding. So the first way is just saying that pressure plus our gravitational energy density plus our kinetic energy density is constant. Right? This is just saying that as water flows through a pipe, the pressure may be changing, the height of the pipe may be changing, the velocity of the fluid in the pipe may be changing, but it turns out this sum of quantities has to stay constant at any place in the pipe, which allows you to solve for an unknown at any place in the pipe. This is another way of writing on the same equation. That's what we already discussed. Right? This is again a statement that this sum of quantities is constant, that this sum of quantities at point 1 is equal to this sum of quantities at point 2. All right, so this is going to be really useful for you when solving problems. I could also rewrite this, just subtract all of these terms over to this side and rewrite this equation in this way, that the change in my pressure plus a change in my gravitational energy density plus a change in my kinetic energy density has to be equal to 0. So this is another nice conceptual way of writing down the Bernoulli equation, because again, if you have a pipe where, say, the pipe gets skinnier, so the water has to move faster, right? You put your finger on the end of the hose, this term gets bigger, right? Our velocity gets bigger. Our velocity at time 2 is bigger than our velocity at time 1, right? If our velocity is getting bigger, something else has to get smaller in order for this sum of quantities to be 0. So if this is some positive number, this would have to be some negative number. For example, the pressure would have to go down. Okay, so this is another conceptual way you can think about Bernoulli's equation. So let's think about a quick clicker question. Again, we've seen this problem. We discussed earlier that the velocity at point A and the velocity at point B are the same based on the continuity equation. So the question is, how does the pressure of the fluid compare at point A and point B? Right? We have fluid flowing in this direction, and as the fluid flows down the hill, what happens? Does the pressure increase, meaning pressure at point B is greater than pressure at point A? Does the pressure decrease, or does the pressure stay the same? Okay, so pause the video, think about that, and then on the next slide, I'll tell you the answer is B. The pressure goes up. The pressure at point B is greater than the pressure at point A. So pressure is an energy density, right? As I move from point A to point B, the gravitational potential energy is decreasing, right? And so the gravitational energy is going down, but the water can't move any faster. The kinetic energy cannot increase, again, because it's a completely filled pipe, and there's all this water in front of the water, so it can't speed up as it goes down that hill. Right? So the only thing that can change is the pressure. So if the gravitational potential energy is going down, the pressure must go up, right, by Bernoulli's equation. Let's do one more clicker question here. If I have an incompressible fluid flowing through this pipe, initially the radius is 2r, and then the radius decreases to r. What happens to the pressure and what happens to the volume flow rate? So take a moment and think that one through. Okay, and the answer here is D, a lower pressure and the same volume flow rate. Okay, we know the volume flow rate has to be the same everywhere on a pipe. If it's a completely filled pipe, it's an incompressible fluid, right? The volume flow rate has to be the same everywhere. But as I move from point P to point Q, the continuity equation tells me that the water has to move faster, right? It has to speed up as it moves from point P to point Q in order to keep the volume flow rate the same. If it's moving faster, the kinetic energy is bigger. Where did the energy come from? Well, the pressure had to decrease. So that extra kinetic energy that's gained by the water is sacrificed by the pressure that is lost in the same action, right? The pressure goes down, the kinetic energy goes up. And you can play around with that FET simulation again. Again, we can measure the pressure at different places on the pipe and check that, okay, indeed, when a pipe gets bigger, the pressure goes up. right? And when a pipe gets smaller, the pressure goes down. Okay, so when you constrict a pipe, the pressure inside that is actually smaller, right? Because the velocity here is bigger. The increase in kinetic energy had to come from somewhere, and it came from decreasing the pressure. Okay, so let's go through some examples of this. First, in medicine, this is an important idea. This could actually save your life, an understanding of what an aneurysm is. When you have a weak blood vessel and an artery gets a little bit wider, what happens? Well, the flow rate in that blood vessel has to stay the same based on the continuity equation. Right? The flow rate in this part of the artery has to be the same as in this part of the artery. So since the artery is getting bigger, that means the fluid velocity is going down. Okay? If the fluid velocity is going down, well, energy must be conserved. Fluid velocity is going down, the kinetic energy is going down, so something else had to go up in order to keep energy conserved, right? Where does the energy go? It goes into pressure. So the pressure inside the aneurysm is actually increased, right? And that's kind of a really bad thing because a larger pressure means a larger force per unit area on the edge of that blood vessel, which means the artery gets even larger, right? So it's kind of this cascading negative effect. So it's a really bad thing. But we need to understand, again, using Bernoulli's equation, how pressure changes in a pipe to understand this. We can also think about a biology fun problem, which is giraffes. How do giraffes get blood up into their brain if their heart is way down here and their brain's way up here? How do they do that? Well, the Bernoulli equation tells us that as the height increases, pressure must decrease, right? If this term is getting bigger, this term must get smaller in order to keep this quantity constant, okay? And what that means is if the pressure is of the blood is getting lower and lower and lower and lower all the way up the neck of the giraffe, that means the blood pressure of the giraffe at the heart level has to be really big to still get the blood all the way up to the giraffe's head. So that means a giraffe has a blood pressure something like 280 millimeters of mercury, where it's more like 100 to 120 or something for a human. So it's more than double the blood pressure of a human. Okay, so giraffes have high blood pressure and they have to. Another interesting example is from engineering, which is the Venturi meter. So if you work in a factory or in many places, if you want to measure fluid flow, if you want to measure the velocity of a fluid, this is often done with a Venturi meter. Right? A Venturi meter looks like this. It's just a pipe with an opening, and then the pipe gets a little bit smaller and there's another opening. Okay, and so as fluid flows through this pipe, the fluid moving through the constriction has to move faster. In doing so, the pressure goes down. And by measuring the pressure at this opening and the pressure at this opening, measuring that pressure difference, you can measure how fast the fluid is moving. Right? So the fluid is moving at some velocity at point 1, it's moving faster at point 2. That means the pressure at point 2 is smaller, which means the water rises less high in this pipe than it does in this pipe. Right, so this height difference translates to a pressure difference, which you can use to measure the velocity of the fluid in the pipe. Okay, so that's another nice example. Okay, so let's make sure we understand conceptually how to solve problems involving fluid flow. And here's a very common type of problem you could see. We have a pipe which is changing in both height and radius. So we have a pipe that has some cross-sectional area, right, some radius, and it's at a given height y1, and then it goes down a hill. And so there's a new height y2, right? The height we'll just mark as kind of being the middle of the pipe, and the pipe also expands. So at the bottom of this hill, we also have a bigger area pipe, a bigger radius pipe. Okay, so the question is, how does the pressure change from point 1 to point 2? If we know the pressure at point 1, we know the height at point 1, we know the velocity of the fluid at point 1. The question is, how does the pressure change as it flows down the hill and as the pipe gets bigger? Okay, so it's a very common type of problem you'll see. So when you see a problem like this, we have to bring in two major concepts. There's actually two separate effects here that lead to pressure increasing. And so first of all, the water in this pipe is incompressible and it's a completely filled pipe. Right? So that means the water cannot speed up as it moves down a hill. Right? Water moving down a hill in a pipe is not going to speed up down the hill because there's water in front of it. Okay, so what does that mean? That means that as this water goes down the hill, the potential energy of the water is going to go down, right? It's losing height, it's losing potential energy. Something else has to go up, and it turns out what goes up is pressure. Pressure acts as like another type of uh, energy, right? Pressure is an energy density, and so we are storing energy in that pressure. The other thing that happens is as the pipe radius gets bigger, the water must slow down, right? So the pipe getting bigger causes the water to slow down, but the flow rate has to stay constant, right? And that makes the water slow down. So if the water is slowing down, where does all the kinetic energy of the water go? If the water is suddenly slowing down, well, it goes into also a pressure increase, right? So we have two separate effects here causing a pressure increase. So how do you solve this problem? Well, first you recognize those two effects, and then we have to bring in kind of our two most important equations for fluid flow. First, if we want to understand how the kinetic energy is going to decrease as I move from point 1 to point 2, right? The pipe is getting bigger. We know the water is going to slow down. So we know that this term is going to be bigger than this term, right? The kinetic energy at point 1 of the water is going to be larger than the kinetic energy density at point 2, right? Because it's moving slower at point 2. So in order to calculate this, we're going to have to figure out what is the velocity at point 2. To do that, we have to use a continuity equation, right? The only thing that really causes water to speed up or slow down in a completely filled pipe is if the area of the pipe changes. The flow rate has to stay constant everywhere. So at point 1 and point 2, the number of liters per second crossing that point has to be the same. And we can rewrite the volume flow rate in terms of the cross-sectional area times velocity. And once we do that, we can rewrite area in terms of pi r squared, assuming it's a circular pipe. And if I know the radius at point 1, I know the radius at point 2, I know the velocity at point 1, I can use this equation to solve for the velocity of the water at point 2, and then I can plug that in here. So now I know this term, right? I know the kinetic energy density at point 2. I can use this term to calculate the gravitational potential energy density at point 2, and we know all of these already. This is what they gave us in the problem, so now I can use the Bernoulli equation to solve for the pressure at point 2. We can see this experimentally. Go back to the video you saw earlier of poking a bunch of holes in a water bottle. There's two separate effects here. I encourage you to use one equation, the static equation, to understand why does the pressure in the water increase as you go deeper. Right? This equation tells me the pressure at a given depth, where P naught is the pressure at the surface. In this case, it's 1 atmosphere. And this is the density of water. This is 9.81 meters per second squared, and this is our depth. So as I go deeper, the pressure in this bottle is increasing, right? And we also know that the pressure outside the bottle is just 1 atmosphere. So inside the bottle, I have 1.5 atmospheres of pressure. Outside, I have 1 atmosphere of pressure. I have a big pressure difference that is going to cause the water to speed up and go in this direction. And I can figure out the speed at which it exits that pipe using our dynamic equation, or our Bernoulli equation. Okay, so this helps to explain the original picture that we started this chapter with. How do you have this massive amount of water with all this kinetic energy coming out of this dam? On the other side of this dam is just water at really high pressure. The water outside this dam is at atmospheric pressure. So in going from high pressure to atmospheric pressure, we're losing all that energy density. And where does that energy go to? It goes to kinetic energy. Okay. You can use the same simulation in the PhET simulations that we've been using to also play with this. Right, so if I have this water tower, I can check that the surface of that water is basically at atmospheric pressure, around 14.7 pounds per square inch. As I go deeper in that water tower, right, the pressure is increasing and increasing. Again, that's why water towers typically have more strength bands at the bottom of the water tower. But I also can recognize that outside the water tower, it's just around 14.7 psi at that atmospheric pressure, where inside it's at really high pressure. Okay, so if I was to open this opening here, I have water going from high pressure to atmospheric pressure out here, and that is what gives it all this velocity. Right? We have water coming out at a pretty good speed, 10 meters per second. Where was it getting that kinetic energy? Was converting a high pressure into low pressure. Right? We're losing a type of potential energy density and gaining kinetic energy density.